Hello, hello. It is time for lecture 18. Yes, 18. Now, if your screen is flipped in one way, then that's 18. And if it's the other way, it's 81, in which case I gotta switch back. This is now lecture 18. This way. Yes, lecture 18. That's what it is. Everybody, I am just amazed at how cool the universe is at this point in time. Remember, we've been filling out this timeline, right? We're trying to get all the way down from time zero, redshift approaching infinity, early on in the universe, getting to today, right? The present day, 13.8 billion years after the Big Bang, and a redshift of 0, the present day. We're still got a long way to go, but remember, we're filling it out now. We're doing really well in this area right here. And we're getting to the point where we now know that there's a tiny bit of matter left over. As the universe continues to drop in temperature, all that radiation, all that energy, right, starting to dissipate. It's all there, but as the universe is expanding, it's being spread out over a larger and larger volume. So the temperature is dropping slowly but surely. And remember the temperature formula, right? The temperature at redshift Z, right, is the temperature at redshift 0 right now, 2.7 Kelvin multiplied by 1 plus Z. So we're getting temperatures down into the billions of degrees instead of the trillions or quadrillions or quintillions of degrees. We're getting pretty down there. It's getting kind of chilly around here, 1 billion degrees, right? Still way hotter, of course, in the center of the sun or the, say, center of a nuclear explosion. So we're still like way the heck off in those kinds of cool world environments, right? So that's a lot happening. But here's where we are. At this point, okay, we can jump to the point where all the symmetry breaking is done. It's about a billionth of a second or so after the Big Bang, right? So from 10 to the minus 32 to a billion, we've broken all the symmetries. We now have 4 fundamental forces. Remember how the 4 forces were symmetry broken this way, right? And it came out to gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force, which still exists over here. I kind of drew it in a different color. It's hard to see, but just you guys can see, right? Yeah, electromagnetic force. So these are 4 forces that still exist now because of those symmetry breaks. And so now, where are we, right? What is the circumstance? Well, let's just write that down. At a billionth of a second or a trillionth of a second or so after the Big Bang, okay? So at this point, about, let's just say about 10 to the minus 9 seconds after the Big Bang, about 10 to the minus 9 seconds, a billionth of a second after the Big Bang, the universe has extra matter in it, right? And so the matter is swirling around with all the energy, but there is a little extra matter there. And that matter, the matter that can survive at a billionth of a second after the Big Bang with the temperatures being so incredibly hot and so forth, is a mixture of subatomic particles, specifically those that have to do with the strong nuclear force. You have quarks and you have gluons. They can sort of exist. They kind of pop out, and in this high temperature regime, high density regime, high energy regime, they are able to exist. And so they kind of swirl around. There are 8 kinds of gluons and there's 6 kinds of quarks, right? So it's a soup is what it is. It's a quark gluon soup. And this is what the nature of the universe is at this point. The quark gluon soup. The universe is at about a quark gluon soup. And then slowly things get a little bit more steady, right? They start calming down. The temperature is dropping still further. And it's dropping down to temperatures instead of billions of degrees, trillions of degrees. It's now dropping down to maybe less than a billion degrees. How about that? Wouldn't that be nice? By around 1,000th of a second. Okay, so I'll say 10 to the minus 3 second after the Big Bang. I'll just start becoming more than 1,000th of a second after the Big Bang. All right. At this point, the temperature is down to under a billion degrees. And now we see the standard model appearing, right? Instead of the quark gluon soup, which is the best that matter can do up to that point, the standard model particles start to form. Okay, so you get all your fermions, you get all your bosons, you get those quarks, you get those leptons, right? You get those various kinds of bosons, the W and Z particles and photons, which had always been very prevalent. Now you're actually getting those other particles. Those fermions and bosons are now very, very well established. Standard model of particles established. Well, I won't say established, but it establishes. All right, it sets itself up at around 1,000th of a second after the Big Bang. All right, so now we're starting to get those subatomic particles. We're made of subatomic particles, right? But actually, remember, you and I, we're learning about subatomic particles because these subatomic particles usually exist only in the high energy environments, right? This is 1 billion degrees. It's just barely under 1 billion, but it's still 1 billion degrees. That's really hot, right? Way too hot for us. Atoms and molecules and so forth don't exist at billions of degrees. Here on Earth, they exist in hundreds of degrees, right? Maybe thousands of degrees, but not billions, not hundreds of millions. What had to happen to go from these subatomic particles to the particles we know today? They actually had to be assembled during this period of time, okay? And that assembly, the creation of nucleons, right? Protons and neutrons, the things that make eventually all the atoms and molecules that we are made of today, that creation of nucleons, right? An atomic nuclei that as a result is a word that you will wind up becoming very familiar with over time. I'm going to write it down on this piece of paper. It's called nucleosynthesis. Nucleosynthesis is, as its name suggests, the synthesis or the creation, the production, right? The assembly of nucleons and an atomic nuclei. Nucleosynthesis, right? This is what begins in this period of time in the universe. Nucleosynthesis starts when the subatomic particles, the up quarks and the down quarks and the gluons come together to start making protons and neutrons. And then those protons and neutrons start to assemble into more complicated objects. Okay, so I'm going to put right here, nucleosynthesis. Really, it starts maybe a few seconds after the Big Bang, but it ends a few minutes after the Big Bang. Why? Remember, the temperature continues to drop, right? As the nuclei are forming, the conditions have to be just right. The temperatures have to be millions of degrees, maybe billions at most, but millions of degrees or so. And the density of those particles has to produce a certain pressure in that environment that makes nucleosynthesis possible. Okay, so nucleosynthesis, it happens from about 1 second, so 10 to the 0 to 10 to the 3 seconds. Now, I would say, right, that 10 to the 0 means 1, and 10 to the 3 is 1,000, right? 1,000 seconds is about 17 minutes. So that's sort of the upper limit of what's happening. By the time we get to 17 minutes, really by the time we get to about 10 minutes, the temperature of the universe has dropped too low for nucleosynthesis to happen. The density of the universe has dropped too low for all those subatomic particles to be able to come together and make atomic nuclei. Okay, so that's too bad. But what happens at the end, right? When nucleosynthesis ends, at the end of nucleosynthesis, after a few minutes, what is left? What has been produced? Turns out this is what is produced. I'll show you, I'll share the screen of the textbook in just a moment, and there's a lot of other sources where you can take a look. But at the end of nucleosynthesis, okay, at the end of this cosmic nucleosynthesis, you wind up with about 75% of the mass in the universe, okay? 75% of mass is hydrogen, is just free protons, okay, is hydrogen. This stuff, H, just single protons floating around in the universe, just protons. Right? Remember, the hydrogen atom consists of a proton in the middle, sometimes with neutrons attached to it, but usually just proton, with an electron orbiting around it, right? So it's 75% of the mass of the universe is hydrogen. Meanwhile, about 25% of the mass is helium. Helium, remember, has 2 neutrons and 2 protons, and they're usually stuck together and they form a helium nucleus, right? And they are floating around now. So 25% of the nuclei that have been formed are just plain old protons. 75%, plain old protons. 25% are these helium particles, alpha particles, right? 2 protons, 2 neutrons stuck together in a helium nucleus. They're called alpha particles. And so you've got helium and you've got hydrogen. The rest of the universe, less than 0.1% of the mass is everything else. And all that, everything else, the less than 0.1% of, variations of hydrogen, like maybe hydrogen with an extra neutron attached to it. That's called a deuteron, or it's the deuterium nucleus. Sometimes you have helium that's got 2 protons, but only 1 neutron. That's a helium-3, right? You sometimes get lithium that's got 3 protons and maybe 3 or 4 neutrons in it, right? So you have some variation of these other things, but there is no carbon, there is no oxygen, there is no gold or silver or iron or calcium. Those heavy elements, they didn't get a chance to form. The only thing that has formed so far is hydrogen and helium. Really? Yes, we're made of more than hydrogen and helium. Where did all the rest of that stuff come from? In future lectures, you will find out. It's pretty amazing stuff, and we will definitely go over it, and it'll be so cool. Right now, let me go to the share screen and show you that section of the OpenStax Astronomy 2nd edition textbook that we've been looking through up to this point. It has a short explanation, but you'll have longer explanations elsewhere on your study guide stuff. Hopefully you're already filling out your study guides and so forth. That'll tell you roughly where we are and what you can learn more about the specific details of the nucleosynthesis that I'm referring to. Okay, so you can see what's happening in this text here. E equals mc squared. They talk about the energy and how things change. Oh, the sun, a nuclear powerhouse. Yeah, if you didn't know this already, the sun actually does some nuclear stuff too. And we'll be getting to that, like I said, in upcoming lectures, but this is cool, right? At a temperature of 6 billion Kelvin, right? 2 photons colliding will create an electron and a positron. And then if it exceeds even more than that, you can make protons and antiprotons. But see how the universe continues to go forward, and it has a temperature at about 100 billion Kelvin at about 100th of a second. And then now, here are the different kinds of diagrams that showing what's happening, right? At about 100th of a second, you're doing all this antimatter matter creation and destruction, right? As the gamma rays make protons and electrons and positrons, and then the electrons and positrons make gamma rays. But then at the few second mark to the 3-minute mark, these are the things that are happening, right? Protons and neutrons have been created. And sometimes the protons and the neutrons combine and make a deuteron, like I was saying. And then the deuterons and the proton will come together and make a helium-3, right? 2 protons and 1 neutron. Sometimes these 2 helium-3s, 2 deuterons, 2 deuteriums will combine to make a helium. Sometimes a helium-3 will combine with another proton to make helium-4. And you wind up over the course of several minutes, right? Minutes, making all of the protons in the universe up to that point. All the matter gets turned to protons, and these cool helium nuclei, and then little tiny bits of other stuff, right? There's still other subatomic particles floating around, right? Things like neutrinos, things like other kind of itty bitty subatomic particles flying around, photons in abundance. Those are massless, right? But they are particles, they're bosons. They're floating around, but mostly that's what we wound up with. We have all this material, okay? Now, you have these neutrons flying, neutrinos flying around, so all this sort of stuff. And you see about the atomic nuclei down to about 1 billion Kelvin, protons and neutrons combined. Read this stuff, okay? Because this talks about how deuterium is useful in our astronomical studies of the universe. But the beginning of the universe and that history is an extremely interesting and important part of how we understand how the universe works today. All right, so read that part. I'm going to advance a little further, if I can, to the next part. See, this part talks about the cosmic microwave background. We already learned this part, but how does the cosmic microwave background get created? Right? Remember that leftover temperature in the universe? Right. That leftover temperature is a really important part. That creation, the construction, the production of the cosmic microwave background coincides with a lot of other stuff that happens in this range. And at that point, see, this is here, we're at 1,000 seconds, right? The temperature is still in the millions of degrees. And we've stopped to here, and this is the end of cosmic or primordial or Big Bang nucleosynthesis. What next? Well, that's the other cool stuff that's happening. And we're going to continue on this piece of paper because we got to get to the present day, right? History of the universe is long. It's got a lot of different pieces. And this is the last part that we'll talk about up to this point, because once we get to this part that I talk about, then we can start building things like stars and galaxies and black holes. Okay, here is where we're getting to be the really stuff that we'll start recognizing. That early part of the universe, we've been talking for these several lectures up to this point about the entire nature of the universe itself, the scientific theories that underpin our very existence. And now finally, right, after going through all of that stuff, Big Bang, Planck time, inflation, cosmological stuff of all kinds, protons, the quark gluon soup, the subatomic particle zoo, all of that. Now we've got protons and we've got helium nuclei, we've got these other particles, and they're swimming around with a lot of energy floating around. Right? Lots of photons kind of dragging all over the place. Well, what needs to happen? That matter has to be able to organize, doesn't it? In order for that hydrogen and helium to make things like stars and galaxies and black holes, it's got to sort of free itself and start acting under gravity to combine into objects. Right now, there's so much energy zipping around all through that you still don't have that kind of freedom. In fact, matter is dragging on energy, energy is dragging on matter. The universe is not transparent. The universe is unable to actually produce any reasonable structures beyond the very, very basic, small, little itty bitty structures, sort of on the level of, like I said, 0.001% variation, right? So this is something that has to happen when the universe cools down some more. Okay, so let me get back to this part here and rewrite up here, right, the time, how much time after the Big Bang here in years, and then the redshift in Z, like what redshift, and then what is happening, the events that are occurring during this time. Okay, so you've got to get down to a temperature of about 3,000 Kelvin before matter and energy, okay, can wind up doing something really cool. You have electrons, remember all those leptons floating around together with the neutrinos and all those sorts of things? And then you have atomic nuclei, don't you? Right, the protons as hydrogen nuclei, and the alpha particles, the helium-4 nuclei, 2 protons and 2 electrons, 2 protons and 2 neutrons. The electrons have to find a way to connect with them. Right? Up to this point, the temperature's too hot. They keep getting dragged away. They keep bouncing off, not doing anything. Once the temperature gets down to about 3,000 Kelvin, okay, hot blast furnace temperature, 3,000 Kelvin, then electrons can start to combine and come together right? They were whatever, they're recombining. They're combining into atoms. Remember our atoms, we think of atoms as nuclei with electrons around. Right now, they're just nuclei and electrons flying all around. When to make them together and actually combine, the temperature's got to get down to about 3000 Kelvin. At what redshift is the temperature 3000 Kelvin? We can now do this calculation. We can at last do that. Remember, we were talking about this. This is the formula that we talked about, right? The temperature at a redshift Z, the temperature at redshift Z, is the temperature at redshift 0 times 1 plus Z, like that. So let's do this quick mathematical calculation. At Tz, at the temperature of Z, we want 3000 Kelvin, right? This is an approximation. It's not that exact, but at 3000 Kelvin, that would equal T0, which is 2.7 Kelvin, times 1 plus Z, right? Like that. So why don't I just do a quick division? I'll divide both sides by 2.7 Kelvin. I'll use a different pen color so that we can sort of see how that's working out. Divide both sides by 2.7 Kelvin. Divide this side by 2.7 Kelvin. So then, what is 3000 divided by 2.7? It's about 1111, right? But I don't want to be that exact because it's about 1100. I'm just going to round. About 1100 equals 1 plus Z, like that. Okay. Now, 1 is so much smaller than 1100 that we can just sort of say that it's very close, right? 1101 is still, not enough significant. It's too many significant digits. That's just we rounded because it was this actual number is like 1111, whatever. We're only going to 2 significant digits, so this 1 is basically incorporated in here, and it's still about 1100. So that would mean that at Z, a redshift of about 1100, okay, that is when atoms form, okay? Atoms, that is things with electrons and protons and neutrons. So nuclei plus electrons together in a single particle form at about a redshift of 1100, 1100, okay? And that's called recombination. Now, really, they're kind of combining for the first time, but they're recombining because they can combine and recombine a huge number of times, many times during the first many years in the universe. But what happens is this kind of recombination is almost like a chemistry term, physical chemistry or chemical physics kind of term, where you actually put them together and they actually exist and stay as an atom. Okay, as a stable atom, as an atom that has neutral charge and things like that. So recombination happens at about redshift of 1100. Okay, and then by cosmic coincidence, right around that same time, okay, somewhere between a redshift of about 1100 and 1300 or so, the universe keeps expanding, right? Remember how the universe was so crowded with both matter particles and energy particles that they were like all stuck to one another and they couldn't separate and have the light kind of stream through the universe and have the matter start glomming together to make stuff like stars and galaxies and black holes and eventually planets and people and things like that, right? That couldn't happen until there was enough space that the particles of light, of energy, could separate, right? They could decouple from one another. Now, you know about when like you're coupling something, like hitching a trailer, like if you're driving a pickup truck and you want to hitch a trailer to it, right? If that's a coupling, that holds these two things together. You decouple it, you unlatch the stuff, and then they become separate, and then they go their separate ways. Hopefully you do that when you want them to go to separate ways, not like when you're on the road and then suddenly the trailer separates. You don't want that kind of decoupling. But the decoupling of the universe's particles of matter and the universe's particles of energy happen at around redshift about 1,000, between about 1,100 and 1,300, really. And like I said, it's quite a coincidence. It happens right around the same time that recombination happens. Okay, so I'm going to write down that here too. Simultaneously, I'll say almost simultaneously, matter and energy decoupling happens. They stop dragging on one another. Matter and energy decoupling. And you have the recombination. All right. These things happen right around that time, around redshift about 1,000, between, like I said, about 1,100 and 1,300. So this is the key point. If you do the calculations, okay, which we're not going to do here, like I said before, but if you do the calculations, what you find is that redshift range, okay, from about 1,000 to 1,300 or so, and we're going to count like down to 0, right? Because redshift 0 is today. So big redshifts are in the past, little redshifts are happening in the range before, right? So from about redshift of about 1,300 to about 1,000, right? That period of time happens to coincide with an age of the universe of about 400,000 years. So 380,000 years after the Big Bang, that's what we'll use as a number roughly, okay? 380,000 years after the Big Bang, give or take, which means that the redshift of the universe at that point is between about 1,300 and about 1,000, okay? The key events that are happening in that period of time: decoupling. That means matter and energy decouple, right? So I'm going to write that down here on our timeline of the universe. And then atoms form, right? Recombination. That's when electrons come together with atomic nuclei to make atoms. Right? So decoupling, matter and energy separation. Recombination, atoms form. And what does that decoupling mean? It means that matter starts to make structures and energy flows freely through the universe now, right? It's still hitting all of this matter, all right? Because all of that matter is still there. It's kind of like a thick fog because the universe isn't that big, right? There's a fog in there. So you wind up with a circumstance where you can't see very far, but the matter, the light, they are separated now. And so you can stream through the universe in a whole different way. And so what is that energy? What is that energy now streaming freely that can fill space, creating a temperature? That's the cosmic microwave background. Yes, decoupling allows the creation of structure in the universe in terms of matter, and it allows the creation of the cosmic microwave background. Cool, right? Yes. So I'm going to write that down. And I'm going to write the cosmic background, not just the microwave background, because at that time, right, the temperature was so high that it wasn't a microwave background. It was a very high temperature. Remember, still 3,000 Kelvin or so. So it's the cosmic background radiation is that time is produced. And since then, it has now become cosmic microwave background. But at some point, it was probably not microwaves. In fact, it was infrared, right? You might have been able to see some of it with your eyes had you been there during that time. But of course, none of us were there at the time. So decoupling, recombination, the cosmic background radiation, that's all a result of what's going on now at around a redshift of 1300 to about 1000. Okay, decoupling, recombination, the cosmic background radiation, that's all this time. At this point here, we can finally start seeing the large scale structure of the universe start to form. And that large scale structure is pretty amazing. You might think that like all the matter in the universe is evenly distributed and that's all, right? It's all like this big, thick, even kind of fog. But remember those different variations at a factor of 0.001%, all those variations in the cosmic microwave background? Those little tiny variations, 380,000 years after the Big Bang, was not only in the background radiation, it was also in the background matter distribution. And so you had little tiny areas that were more, little tiny areas that were less dense, right? Those little tiny areas actually made a difference. Now, 100,000 to 1, all right, you have to realize just how flat that is. Imagine if all of New York City, Staten Island plus the other 4 boroughs, okay, this is about 300 square miles, right? Imagine if this entire city, all 5 boroughs, were a sheet of perfectly smooth glass, right? Perfectly smooth glass. If you're trying to make a 0.001% variation in the height of this compared to its area, what you actually have to do is to take this big, huge area, right? Which is like 50 miles in every direction. I mean, it's a big triangular kind of space. It's really big, right? Getting around it, it's complicated. But if you're trying to get through it, imagine taking a handful of sand and throwing it across. Just gravel, okay? Like really fine stuff. Throw it across this entire city of New York. That's the variation between a sheet of glass, perfectly smooth, and just a little bit of gravel spread around the entire 5 boroughs. That's the granularity of the matter density and the energy density at that time. That's it. Whereas the energy density is preserved, right? Because it's spreading out through space and it's spreading as time goes by and getting cooler and cooler and cooler. The gravity that the massive particles generate, they go in an opposite direction. When you have a little bit extra mass in some location, the density is a little bit higher, then more stuff falls into that part of space, right? That's that dimple caused by the general relativistic effects of gravity. So those areas start getting more dense, more matter starts to collect. Over time, those areas get more. If there's a little streak, okay, across this super smooth sheet of city glass, there's a streak, like a little stream of gravel, little pebbles, little powdery bits. That stream will start collecting other little powdery bits that are not quite as densely, and they'll come together into this big structure, right? Eventually, over time, you wind up forming a large scale structure of the universe, which kind of, it doesn't look like it's evenly spread out. It actually looks kind of like a web. Looks like cobwebs, maybe looks like sponges or something like that, okay? There's a lot of really cool stuff that happens, and it's not what you expect. And so in this timeline here, this is where we start describing what happens, starting around redshift 1000 or so, up through what we're ever doing otherwise. Large-scale structure of the universe starts to form, okay? Now, to be fair, large-scale structure already starts to form before this happens, or more accurately, the seeds of structure start to form, right? So, but the seeds of structure are different from the actual large-scale structure that forms during this time after about redshift of 1000. Now, we often hear of this being referred to as the cosmic web, okay? And if you do the study guide viewings of the other videos and the other reading that I want you to do during the rest of the study. I hope you're filling out the study guide right now for some of this stuff. But the large scale structure, the cosmic web, you will see, okay, from this redshift of about 1,000 up to the present day, how does matter align itself? How does matter do what it does, right? That's all a really cool thing that you can simulate using supercomputers and seeing how that matter collects. And now is the time where I have to throw in something that is still mysterious. Yet another unusual puzzle which will work on our things, explanations and understanding of the scientific theory that is the Big Bang, that does describe the creation of the universe and what happens afterwards. The evolution of the universe is the right way to put it, right? Turns out that all those particles, those protons and neutrons and electrons and neutrinos and things like that, they're really good at making us up, right? But the amount of gravitational pull in the universe, the amount of matter in the universe far exceeds the sum total of all the protons and neutrons and electrons and neutrinos and other particles in the universe. Isn't that strange? Yes. In other words, these particles, right, the standard model particles, which we've been talking about up to this point, they're really good at doing those forces that we referred to, right? The four forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, those things with the spontaneous symmetry breaking and all that, that explains stuff really, really well up to a point. But when we measure how the large scale structure of the universe is put together, turns out there's a lot more gravity than would be predicted by just the standard model and these particles. Okay, these particles here, the fermions, the leptons, the gluons, the electrons, muons, tauons, the quarks, the bosons, the all those guys, and the cool dude Murray Gell-Mann, right? All those things that were put together back in those days. For all of the effort that they did, it's less than 1/5 of the actual total amount of matter in the universe. Can you believe that? Add up all the protons, all the neutrons, all the electrons, and you figure out like how fast things are moving and how they're gathering together, the total mass in the universe, it's only about 1/5. The other 4/5, heck, maybe the other 5/6, large amounts of matter in the universe, right, is not made up of protons, neutrons, and electrons. This is a very strange and unusual thing. It's been experimentally confirmed over and over again. This stuff exists, but it's just not made up of any particles that we understand. It's not in the standard model right now as we know it. Okay, so this idea of cosmological dark matter is worth putting right in this timeline, because the dark matter is the stuff that's not made up of protons, neutrons, and electrons, but that's the stuff that drives the large-scale structure creation of the universe. The development of the cosmic web is driven by cosmological dark matter. And that's one of the outstanding puzzles in the contemporary theories of the universe today. Where does this dark matter come from? What is it made out of? People have been trying to detect dark matter particles for decades now, all right, using the same kinds of facilities that they used first to detect solar neutrinos and things like that. They put these big detectors deep underground, pure water, pure other kinds of fluids, lots and lots of sensitive detector equipment. Haven't found a single thing yet. So dark matter remains a tremendously interesting mystery. But we know it exists. We just don't know anything about it. It acts like matter in every way when it comes to gravity, when it comes to Newton's laws of motion. It just doesn't act like matter that we know in other ways, like protons and neutrons and electrons. A tremendously cool mystery. But think about it. If you realize that our universe, right, our part of the universe, that stuff that we're made out of, is just a small fraction of all the matter in the universe. And this matter in the universe is itself only just a small fraction of all of the energy in the universe, right? We are in some pretty interesting environment. That's pretty cool, isn't it? Yeah, it is cool. But from there, from this point, as the large scale structure develops, small scale structures also develop. Right? As the large scale structures build, small scale structures build. And what are small scale structures? Small scale structures are like, oh, I don't know, stars, galaxies, black holes, right? Because we have all the raw materials now, right? Going through all of this history of the universe, from all this stuff down, 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 down here, right? And now we finally got to down, down, down to here. We have all this space left to make stuff, right? Right now, spread out throughout the universe are lots and lots and lots of things, little particles, gas particles, maybe dust particles, right? But they're spread out and they're starting to gather, and they're gathering into blobs that will start doing wondrous things. And that is what we're going to be talking about in the next lecture. So be prepared. We now know that the universe is ready to make cool things. And now we're going to show you how those cool things are made. It's that little extra tiny bit of matter, right? But that matter is powerful stuff. We're made out of it. Yeah? And you take that matter and you start letting gravity do its thing. And then soon, not just gravity as a force, but the electromagnetic forces and the nuclear forces start getting into it. And you start getting cool things like stars and galaxies and black holes. And I look forward to telling you all about those cool things in the coming lectures. Okay? All right. So thank you so much for your time. I really, really appreciate it. I hope you've been filling out your study guide up to this point. Remember, there will be things in the study guide later, including reading from the textbook, some of which you've already been doing during this class, but also other stuff. Okay? Other videos, other writing. Remember, do those things. You'll be setting yourself up to understand the universe. And then when we get to stars and galaxies and black holes and stuff, boy, will you be ready. It'll be awesome. It'll be so much fun. Thank you so much for your time. With any questions, ask me, ask your recitation instructor, ask your lab instructor. I can't wait to go on to the other great stuff. I wish we had 2 semesters, 3 semesters, 4 semesters to tell you all the cool stuff about the universe. But we'll just go with what we have. And I will give you as much as I can in that period of time where we can enjoy and appreciate the universe and its contemporary theories together. Okay? Thank you so much. See you again at the next lecture, all right? Thanks a lot. See ya.